nowhere around here because there's no brick now that they tore down the Veterans Hospital.
Only brick they got is on the ground. Legacy brick.
Stone.
This is going to be what they make buildings out of.
There are, I think, still buildings in downtown Palo Alto that have signs on the front saying, you know, this is a building that's made for masonry and it's going to fall down in the next earthquake. So
We are live now.
Oh.
4-minute warning.
Is that good? Did you like that?
Yeah. We'll be starting in 4 minutes.
Did you send emails to everyone saying?
I have not sent the email. That's what I was going to do.
Okay then. That was easy. You only have a
We now have a legitimate address.
I think the last announcement.
SVFIG. That is.
That's big news. Do you have, Kevin, do you have any announcements?
Get up and start talking.
I'm going to do it from here.
Say who you are.
I know. I'm waiting the cue from Kevin to start.
I was going to use my phone for that. As soon as I remember where my phone is.
As long as somebody's going to check the stream, because I haven't checked the stream.
Anyone see the total eclipse?
Not totally, no.
I saw it on TV.
I saw the picture from space.
Yeah, my brother was up there, but he came back early because he couldn't get a vehicle. He couldn't rent anything, either rooms or.
Yeah, there was
Yeah.
nothing. There were people's backyards where you could put up a tent. Your tent.
I rented a personal on a community college soccer field. So.
Yeah.
They were well prepared though for it. I mean, they actually were, they parceled it up and set up the first
Did they
aid
have
station.
toilets even?
Oh yes.
Wow.
Yeah.
Even better.
It was $100, but
It's a self-solving problem.
Yeah.
Oh look, I've got a alert from YouTube saying that Dennis is wonderful. I knew that already, of course.
I was debating whether it should be SVFIG, but nah, go for it.
You did it. You get to decide.
And I chose that name. It was what they chose first, so I let them have the choice.
Okay, just waiting on Kevin's cue to start.
On YouTube.
Fourth Interest Group now has a vanity name. Silicon Valley Fourth Interest Group. No spaces.
No spaces.
Yeah, so they just put Kyle like four quadrants.
So did you register?
Yes.
Awesome.
Yes.
Yeah, they don't have PKs.
But it didn't change it while I was broadcasting, so the morning is still the open.
It's time, Dave.
Okay, good afternoon, everybody. I'm Dave Jaffe, and I attended the Vintage Computer Festival at the beginning of the month with lots of other people. Took some pictures that I'm going to show you now. Oh, works better when you turn it on. Okay, you get a program guide. You get the inside of the program guide. Lots of speakers on both Saturday and Sunday. Lots of vendors whose wares I'll be showing. Lots of exhibitors. So I was one of the first people in, and it was a good opportunity to take pictures with not a lot of people around. And I'm going to need the help of people here to describe some of these things for me that I don't know, like this stuff. Yeah, okay. Okay. This is a maintenance panel for a computer. It had a lot of flashing lights on it, and I'm not sure. Oh, I think this was an emulation, a software emulation of a real, mock-up, but a software emulation.
Real maintenance panel hooked to a computer that wasn't the computer
Right.
it was meant for.
Why did those come on?
Why don't we turn it off? That might help.
Why did you do that? Okay. Okay, that's higher contrast. Okay, so here's the guy that's manning that maintenance panel. Yeah. Let's see. Yeah, New Bear Computing Store. Again, I'm not sure what kind of computer that is. Yeah, it could be a 6800 computer, little boards that plug into a. Yeah, commercial. Okay. This looks like an IBM. I'm not sure. This was a really interesting exhibit. So these two women had bunch of storage media from all the way back. So this thing was a drive, 20 megabytes. So inside here, there's a giant floppy that spins around, and there's a whole mess of other storage media, iOmega, a zip drive. Excuse me?
Any core memory? Elsewhere, but this is all flexible media.
Yeah.
It's not whatever hard plastic.
Don't copy that floppy. It's a DVD. Zip drive. How many people remember zip drives? Yeah. Floppy disk drive. iOmega pocket drive. These are very thin drives that would fit in the slot in a laptop. This Olivetti thing was sort of the same thing. It was a miniature platter without an enclosure or sleeve, and some, I guess,
8-inch floppy.
5 1/4. This is an 8-inch floppy behind here. Olivetti mini disc, 3 1/2 inch. Other diskettes that just worked for specific hardware. Yeah, different, 3 1/2 inch style flop media that worked in specialized computers. There's a 2-inch one that worked in a Zenith laptop. I don't remember that. How many people remember the stringy floppy? So that was actually a cassette tape type of mechanism. I saw a bunch of these working, and they try to make 4 of them work sort of together. And there was a mechanism where you can put a directory on the front and data someplace, down the line on the tape. And so they made a whole system that basically was analogous to what a floppy drive does, but in a serial fashion. So it would fast forward to the beginning of the tape to figure out where on the tape the program that you requested was, and then it would fast forward into the tape to find where the data was. It was very slow to tell you. I remember using these flopticals. These were 21 megabyte floppy disk drives, exact same geometry, but the media was better, and I think you needed a special, obviously needed a special drive to read that. So those were around for about a year or so. There's another 8-inch floppy.
The original floppy was the 8-inch.
Yeah. Yeah.
Why so big?
Why so big?
Yeah.
Well, everything starts out big. So the thing.
The reason it was that big was if the packing density was low enough and had to load the entire microcode for an IBM, I think it's 360 or 370, which is what it was developed for. The whole microcode to boot
Okay.
the
Yeah.
computer. One that took like what?
Right. So they're saying it was originally invented by IBM. There were two versions of this. As the disk inside the enclosure rotated, it would expose a hole through that media that could be used as an index hole. So it tells you where the start of the data would be. And in hard sector drives, there were actually 32 holes in it and an index hole between two of those. And so with the proper decoding, you can figure out which was the index hole and which were the sector holes. And on the drive itself, it had a track 0 mechanical switch that when you moved the head to that position to activate the switch, you knew you were on track 0. So that's how those work. The original density for one of these, single-sided, was 243 kilobytes.
Yeah.
And later on, they had double-sided, double-density drives. So this was around for quite a while.
200 or 128 kilobytes?
No, the 128 kilobyte one was the 3.5-inch floppy drives. But the 8-inch ones was 243K. But that went up to maybe about 1.2 megabytes if you did double-sided and double density.
Still using nuclear arsenal.
Oh boy. Okay, string. So this is CBM stands for Commodore Business Machine. So this came after the PET computer, a little bit more refined as far as the keyboard was concerned. Here's the original PET with an enhanced keyboard. I think I have a picture of one with the chiclet keyboard and a tape drive on the front. This is an interesting project. This is a project to put CPM hardware on a very small board. And I think Alice 4 is the current state of their project right now. But I think this is just the keyboard and display that they were using. And here's the hardware. It's about maybe 3 by 4 inches and multiple layers. And there's actually different processors on there. One to generate video and one to operate the keyboard. And I think there's a flash drive you can plug in here. So it's actually pretty nice if you ever wanted to revisit that era in time.
They have a Facebook page.
Yeah.
GitHub.
Right. This is the Monster 6502. So this is a giant board And let's see, this one has chips on it, but there was also a version of this at the Maker Faire where all the chips and CPU were done by individual transistors. This one is done by individual chips. So
He says monster, but it's like 14 inches.
yeah,
The long edge.
yeah, yeah.
This is like the old days, was it Schottky-based TTL chips? Because I know you could build your own bit slice using that.
Right. Well, I think these are.
181.
Yeah, I think these are just TTL chips up here, and they said that theirs had a lot of LEDs on it to make it look spiffy. And so if you take a look at this, you'll see that they made it look like a chip with pads on the outside here and stuff like that, with LEDs for each pad to tell you if the pads were on and off and stuff like that. But apparently it ran 6502 code. Here's a little keypad mechanism, and it actually running FIG fourth on it. So that was the only fourth related thing at the fair. So, but it's something. Yeah. Let's see, the keyboard is Panasonic. So this was a part of a video game that the kids could play. This looks like God, what is this? I don't know what it is. Yeah, well, this is a CD drive and a floppy disk drive. These may be just Japanese computers. There's a digital PDP-8M. Okay. Yeah, so yeah.
No, that's the real thing, dude.
Yeah. So this is
flip chips there.
No, flip chips was in an earlier version. So this is S100, and so this is a bus probe. This is an S100 board. You plug it in, and you can debug the hardware of your computer made by Jade. And this board over here is a non-populated, and this looks like a motherboard for S100 motherboard. Backplane. Yeah, so I remember these. Bunch of more S100 boards. Yeah. Here's one with SD cards on it, which I haven't seen before. Another one with SD cards. Yeah. Yeah, motherboard. Here's an S100 computer. This is the front panel. It looks like an MSI front panel, and a little S100 enclosure with a motherboard in it. And here's this board on an extender and the front panel and everything. And yeah, these guys were up and running. And these boards usually came in kits. This is a prototyping board where you can, add your own circuitry in here. But typically the memory cards and any other cards you get, you had an option to build it yourself. So that was a lot of fun for me. So this is what started it all for me. This issue of this magazine, January 1975, it had the original Altair on it. Actually, this is a fake just the front panel. You'll never see a front panel for an Altair that's white. So this was a faked front panel. But when I saw this on the newsstand, I remember this. It said, "Oh, this is something I want to get into." So I bought an Altair kit and built it up over the years. It came with at that time an 8080 CPU was going for $395, and they were selling the kit, which included the enclosure, the motherboard, the CPU, and a 256 byte memory card for $397. So that's what got me started. This is an IBM daisy wheel printer that's hooked up to this front panel board here, and So there's a working computer, a traditional computer behind here generating all these lights and stuff. And so they actually hooked it up so that each light can be on, off, or be varied in brightness. So if it was like incrementing through a program, it wouldn't be totally bright or totally off. It would be halfway in between. So I forgot the CPU that this was representing, but he showed how he was able to single step through a program to show how it worked.
And the lights really flicker like they're
Yeah.
on.
Yeah. So the idea of his purpose in doing this is to sell this to a museum so they would be able to have this on display. So it wasn't, there is a profit motive for him doing this. Here's some additional S100 boards, dual floppies, H19 monitor. I built a few of these as well. Another S100 CPM style computer. Couple M-size, yeah, I remember those. An ADM3 monitor, yeah.
And that's what I worked on in graduate school.
Yeah.
I had digital signal processing, I believe that.
Yeah. So John said he did digital signaling processing, and this is to get rid of the dust. These are miscellaneous boards, maybe from a supercomputer or something. I forgot.
That's from a Cray.
Cray.
They're potted and they're selling them.
Oh, okay. Thanks.
Memorabilia.
Right. So this is the backside of it. Looks like an IBM style PC. Oh yeah, this was a CPM single board computer and disk drive, other disk drive over here. He wasn't able to have it boot CPM, but he had a monitor running on it.
It's a big board.
Yeah. Oh yeah, that's right, a big board. This is a K-Pro 2 5¼ floppy drives running CPM, nice metal enclosure, CRT display. Yeah, so this is the Mic 3 computer, which I'm not sure what it was, or at least the keyboard for it. And I guess there's a bunch of boards that went along with that computer. Okay, so this is a IBM PC, but this is not the original floppy disk. The original floppy disks were full size. The original PC had 1 or 2 floppy disks, and it wasn't until later that they added a hard disk drive over here. I think at the low end it was like a 10 megabyte disk drive.
No, it was 5 megabytes.
5 megabytes? Okay.
Yes, and later on they had something called a hard card.
Right. So they had a hard card, which was a hard disk drive on the board that plugged into the IBM. Yeah, I remember that. So here's an early pet with this chiclet keyboard, and this is a cassette tape drive for storing your programs. So the idea was they were able to have an all-in-one machine, because back then you had to have a separate keyboard and you had to figure out how to save your programs and stuff like that. So this is like an all-in-one, again with a CRT up here. Apple II with a monitor and a couple floppy drives and a joystick.
What's the cable?
I don't know what this cable is going to.
Connect to a printer?
Oh, yeah, it's for the joystick. Yeah, okay, it's a joystick. It looks like it goes in the back too. Yeah. So this is a Lisa. It sold for about $10,000 at the time, so it was had a nice nice display, but it was a little bit before its time. They couldn't really, they didn't sell a whole lot of these. But so if you have one, it's actually worth a lot of money. Oh, this is a Tektronix. So this is an interesting display. It had a persistence on the display so that you can actually put something on there and it would stay for a while or retrace it for graphics.
My first job was to do a rasterized version of that.
Yeah. And the neat thing about this is it had this DC 300 tape mechanism built in to save your programs and stuff. Yeah. So this is a very nice commercial computer way back when. I don't think any hobbyist had
More of
these.
a display terminal than a computer.
Right. Okay. Radio Shack machines. Yeah. Oh, this is a Commodore. So all the works were in the keyboard and you hooked it up to your display. And I'm not sure if this one had cartridges or what. I was never a Commodore fan, to tell you the truth.
If you look on top of that, there was a CMOS cookbook and a TTL cookbook.
Oh, yeah. So Apple II GS with a mouse. Not sure what this is. Can anybody read what that says here? No? Okay. This is some kind of game machine. Kevin, do you remember? I don't know. All black. This is an Alto computer. This is a cartridge hard disk drive. This is what the cartridges look like. So this is what Steve Jobs saw and copied as far as the graphical user interface. This is a bunch of keys that you can press with your left hand, and the mouse was over here. And this particular mouse had to travel over a grid. It was had a couple of LEDs in there and would, count the number of lines that it passed over, both in the horizontal and vertical positions. This was on paper, but I had a mouse that actually was metal, and it had red lines and blue lines, and because it had that, it was able to pick up the mouse position. So this was also a network computer with you can have a bunch of these all in an office, all hooked up together. This is the data cartridge. They started out at about 5 megabytes. And went up from there. Some other cards. I'm not sure this one was. Here's the. This is the mechanism that the cartridge slipped into. This door flipped open toward the front. You'd slide that in. You'd have to wait a while until it spun up to speed before you were able to use it. And also when you wanted to take the cartridge out, you had to tell it to spin it down, and then you can remove it. That's what all these lights were for. San Leandro Computer Club. They're into Atari computers. Lots of them here.
It's like various generations of the Atari ST and Stacy.
Yeah. This is an early Apple laptop. You have that one? What's the model designation on that?
We call it a
Power
Power PC.
PC. Okay. Yeah.
Call it a PC back then.
Yeah. And this is apparently another Apple laptop. I think I can sort of tell by the display here. Yeah. Oh, this is a Kim 1 card on the side, and the schematic for it. And this is another one in blue. And this is the fingertip of Dwight Elvey, who created this card, which was able to, I think among other things, add more memory and a monitor to to the Kim 1 to make it work a lot better. So he actually laid it out using a CAD program, and on Sunday he gave a talk there about how he did it. Right, Kevin?
Yeah, I think that there's a chip that you can't get for the Kim 1 anymore, and the purpose of his talk was how to use a chip that you can get, make a board to plug that into, and then you plug the board into the socket where the chip is supposed to go, and have a working Kim 1, regardless of whether whether you can still get this chip.
Okay.
But his exhibit was debugging and diagnosing failures in Kim 1, and I think he went through 8 or 10 of them that, some of them had nothing wrong, and some of them had problems that he was able to diagnose. It was pretty cool.
Okay.
Where else would you go to have, a supply of Kim 1s to fix?
Yeah. So here's an Atari computer with an early graphical user interface, it looks like. Still has a floppy disk in here. I think these are, these are from the table I showed you earlier, where this the Atari, the Atari Computer Club. Just close-up versions of that.
They have actual meetings and stuff.
Can't see that one. Okay, I think this is the consignment area where people can sell computers. These are a couple old laptops on the right here, clamshell types. This is a Heathkit trainer board. So there's a proto board here, and it looks like there's a CPU here, and so you can wire up this computer chip to do things and toggle in a program. Yeah. Okay. A couple early Macs that must have been out in the sun for a while. They're sunburnt. Yeah. 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 I think this is this could be an HP machine, and as I recall, there's a couple floppy disk drives on the side here. A pet for sale. This is an HP 85. No, I'm sorry. Logic analyzer. Behind it is an HP 85. That's right.
RL02 disk.
Yeah.
Over to the left of the logic analyzer.
Oh yeah, disk pack. Pet computer. K-Pro on the side. And pedestal. I'm not sure what this is.
So Zenith.
No. Oh man. Yeah. I don't know what these are. Yeah. This is the HP 85. So it was nice in that it had a screen, a printer, and stuff like this. And it was actually, sold as a professional computer for people.
Last year there was an exhibit where a guy had a couple of these going.
And I think this is a board that's inside there. Oh, yeah. Didn't somebody read? Right. Yeah. I think there was a teardown on an HP 85 online that showed the internal mechanism of this. It was actually very well constructed.
On YouTube.
Yeah. I think this is a CPM machine with a display and floppy disk drive. Or again, I forgot. This is an old Apple laptop, Sony laptop, a couple floppy disk drives, typical 8-inch drives. Intel had their own development system,
Yes.
and this one was an 8-bit development system.
About $30,000.
Yeah, they were very expensive at the time, but they used there was one that had 8080, there was an 8085 one, and there was probably an 8086 version of these development systems. Slide rules.
So that sort of yellow-green on the pickets there, that's 5,600 angstroms.
What's this?
So you needed to know.
Okay. Okay, here's an original IBM PC.
Yes.
And yeah, this is all original stuff. Yep. MSI. This is a model 100, but this was a model 102, which is a little bit came out after the model 100. So this was an 8085 based laptop with a 4-line screen, and it had a way to connect to modem. No, it actually had a modem built in, so you can hook this right up to the line. And these were very popular with news reporters, because they would write their story on the site and then connect back to their office and upload their story. It ran on 4 AA batteries. It had like 32K of memory total. And I actually had 4th running on this one. Well, I had the NEC version, which is very similar to this. It had BASIC on it. That's how you interacted with it in BASIC. Yeah. And I think the guy, I forgot how much the guy won for this, maybe $150, and it still worked. Apple laptop. More Apple stuff, obviously. This is an Apple device that looked like a server or something.
Yeah, it's a Mac server.
Mac server.
And very rare. The biggest Mac in the world.
Yeah. Apple II, Apple IIc, Apple II GS, more Atari stuff for sale. Atari printer. This is that close-up of the mouse. It's an optical mouse that sensed the horizontal and vertical lines. And this is the core to keyboard. Yeah. It's a Nixie 2 clock or something like that. Southwest Technical Products 6800. They had a bunch of plug-in boards here. So this is a Zilog computer, and I actually used these when I was at the VA. It had a Z80 in it. It had a bunch of IO boards. It had these 2 floppies. There was a conversion mechanism that changed a ROM in there, so you were able to run CPM on it. So it was actually a very nice computer that I used for quite a while. So it was actually surprising to see it being on sale. So Osborne computer, bunch of calculators. And this was in the PDP-1 demo room downstairs. So they, restored this. They have it running, and the demo program that they show is Space Wars. So a lot of it was on paper tape, but this computer uses core memory. So once you put a program in core, all you got to do is jump to it, even after you turn it on. So there was a bunch of people in there getting a demo downstairs to have this working.
You could go today and see.
Yeah, this is an ongoing exhibit.
Demos are scheduled when they have people, to the extent that they have people available to demo it. It's it's a computer history museum exhibit rather than part of the Vintage
Right.
Computer Festival. But you can, a lot of the time you can go hear about Space War from the guy that wrote it.
Yep. And this is a picture that Kevin took the following day of Dwight, talking about his Kim 1 project. Okay. That's it. What?
We have a question from the audience.
Okay.
Were there any RCA 1302 COSMAC chip-based computers like ELF 2?
No.
No. Answer
Is
is
that the
no.
one with the little dog on it?
So I remember those. They had a couple like D-cell batteries to power the whole thing.
They didn't have an Apple One there.
No Apple ones. I think last year they had one in the lobby.
That they gave
Boy,
away.
that they,
It
yeah.
was a big fundraiser.
Yeah.
It was a raffle prize for a big fundraiser that they had.
That's been a very big one, you know, those gone for $1 million.
Yeah.
Apple One. Yeah.
Okay. All right. It's a lot of fun. So, this was the second year they've had these after returning from a few years of break. And so it's under like new management now, the Vintage Computer Festivals.
Yeah, we're going to take a couple minutes break.
In your computer.
Yeah.
I see. You didn't show the,
So if you go to the bathroom, now's the time.
Who's up next? Who gets the microphone?
who's up next?
Oh, James, here's the microphone. Kevin, here's the presenter.
Thank you.
Thank you so much.
This problem was getting the to the screen because this was that's okay, HDMI. They say, okay, HDMI, I'm not going to steal your copyright material, but then you decide, no, I think it makes more sense to just put up a so could be a better way of getting although I'm not, I don't want to speak for Brad. I don't start hanging out and talk to you. Apparently that's what they do at Google. Open machines. I talked to him at least once a week. Put something up on the screen of the conference. Oh, they hang out. Oh, they hang out. Yeah, only this projector. This is an older projector. I wasn't the older one because they're for all the HDMI conversation.
Oh,
I had forgotten the reason.
You could get the smaller monitor that spoke fluid HDMI. You can get that to work here.
yeah.
The internet, I think.
It wouldn't be worth that. Yeah, still.
It would, 1% of Apple would just say,
Actually, no, it would be more. Remember, the earlier you are in getting companies, that would be more like Class A, Class B software programs. And as they add more professors, then goes Class B, C, D, E, and that gets smaller and smaller. This stuff, you would have got every Friday. Filthy. You know, it's funny. I live in Las Vegas. That's my permanent address. I moved there for one reason, to protect purposes. Because it's getting so nutty here. I live in Las Vegas. Yeah. Yeah, I have property in Las Vegas. My apartment is in Las Vegas.
I just figured you did it in a more subtle way.
Well, and then,
That
okay, I'll do it
doesn't
again. I'll do
involve
it
turning
again.
everything off. As I utilize the three guiding principles of zeal, ignorance, and brute force. That's the live stream, yeah.
Well, if I work here, yes, but there's no, here's the other thing.
Yeah, this is why I got this picture so much.
Las Vegas.
I think they have ones down
I'm gonna come back like every 3 months.
I think just advance it. The thing about this is that I give it to speakers that know what's going to happen. Okay, there are two buttons, forward and back. Get over it. The laser's the one that says green.
CRP, yeah.
I like it for shaper. Right laser. Yeah.
Oh,
I was gonna buy just a green laser, but a nice one costs more than this.
yeah, that I won't do.
A nice laser, because every bit is nice as the pen. All that for twice the price.
struggling, getting that
Power, yeah. Anything that has CRP, I'm not just gonna think it's for me, it's only a 4 hour. So I do that. My classmate actually showed me keep up.
They used to have a flashlight.
I went there, so I got all the
Replace the. I know the CRP. Remember that backlight? Inside a little voltage converter in the LED. One like that. That's Sinotone.
Ready?
See the way this Confederate statue comes down with just a tiny tug and then crumples up like a paperclip when it lands? Why does it fall apart so easily? Because it was mass-produced. Quickly, cheaply, and most importantly, for a very specific purpose. Take a look at this timeline of when Confederate monuments went up. You'll notice that the bulk of them didn't go up during or even shortly after the Civil War, but during two specific periods.
It came at the turn of the century when white Southerners were attempting to disfranchise black people, and the second burst came in resistance to black civil rights and political rights in the 1960s. It's it's very predictable.
Instead of paying tens of thousands of dollars for a granite or a marble statue, a
Let's make sure it's gone before we start James up. Well, delay. Say something, James. Test,
Something.
test.
Test. Hello? Hello, I'm James Bowman. I showed GA144 last month loading some Flash, and this month there have been some further developments which I'm going to talk about for a few minutes. So a few weeks back, Michael and Mark, who've been at earlier meetings, pinged me about getting GA144 doing something useful, like maybe even, to reach for the stars, showing the current time of day. Now, at first I thought this was just a crazy dream, but we're about halfway now, and it looks like it might actually happen. So watch this space. But in the short term, I'm going to talk about getting arbitrary code running on the GA144. That is an execution environment which isn't limited to running on a single tiny computer. The GA144, if you haven't seen it before, is a great big array, and you think, wow, look at all those computers. I get 144 computers for $10. What a bargain. Until you see what kind of computers you get, because they're not actually that great. Each of them has 64 words of memory, 64 words of ROM. They have a tiny stack and a speedy but quite small CPU. So they're ultra minimal. So as soon as you try to put anything bigger than a triviality on one, you run out. You have to work on two. And that gets old pretty fast, because taking your program and stretching it over multiple computers, distributed programming is hard, as we probably all know. So with 144 of them, it gets really hard. That's what a single node is on the GA144. It's only got connections to its neighbors. There's no global bus on the GA144, so you can only talk to your northeast, southwest neighbor. And the crucial feature of this CPU is that you can execute code from your neighbor. So as well as executing code from your onboard RAM, like a regular computer, you can actually literally jump to an I/O port and execute whatever comes in over that I/O port. So if this node sends data over its bus here to its east neighbor, that neighbor could either read the data or execute it. Code and data doesn't care. And this is kind of a key feature of GA144. Actually, I need to mention, that's how GA144 boots. When GA144 starts up, all the nodes are empty. They're all sitting there just waiting for instructions. A single node gets the boot sequence, and then transmits it to every other node on the chip.
Green button there.
So typically a node on the north side of the chip will get the data, and then it sends it to a southern node, and then it passes it along until every other node on the chip has been booted. And that's how GA144 gets started in the morning. So thinking was that we could build a Forth or a C executing code directly from Flash. We wouldn't take the approach that Polyforth on the chip, the one that Green Array supplies, takes, and a few other projects that I've actually talked about to SVFIG years ago, of building a virtual machine, where you make up a machine, and then you write an interpreter for that machine on a node, and then you interpret the instructions in this imaginary machine, because the interpretive overhead of Polyforth is a hit of about 200x. That is, the difference between writing native code and writing Polyforth code is a factor of 200 performance. Seems like a very big hit. And it's a strong incentive to write your application in 2 languages. If you can write it in high-level Forth or write it in code words, and it's 200 times faster. That's a big incentive to split your application across 2 languages. What if we could build a machine which executes code much quicker and didn't use external RAM? Polyforth runs out of RAM. So we take an approach where the flash chip, which is external to the GA144, is connected to this node, which is in charge of fetching. The fetch node pulls things out of flash, just like in the bootstrap procedure, and sends it to the southern node, which executes the program. And that node then tells the flash chip where to fetch from next. That's the difference. So in booting, it's simple. It always comes from 0. In this, it's just the same, except it comes from the address that this node tells it. It's a tiny change, but suddenly you can arrange flash like this. This is, if you like, a program written in flash. Here is where it starts, and this is the top of flash going. These are chunks of 64 bytes going down. So this is 64 bytes wide, and these are, we call them fragments, right? So there's a fragment here at 0. This is the boot fragment, but it comes up, and as you can see, it's got a length. It's 3 long. That gets sent down to the southern node, to node X. X executes those 3 things, and as its final act, it sends a request for the next fragment, which could be 1 or it could be 5, and so on. 5, the last action of 5 is to request the fragment which it wants to run next. These are all linked together in a great big chain or graph, and that's what makes the program. So the entire program consists of these fragments written into flash. They're all variable length. There's a huge amount of wasted space. I'll talk about that later, about space saving. For example, here, fragment number 7 is really long, and it overflowed 64 bytes. But no problem, we just overflow into the slot, which would have been 8, and the next valid fragment is 9. So the whole thing is made out of these variable length units, which are randomly addressable. You just multiply this number by 64 to find out the byte address where to fetch it from. What would a program look like if you break it up into these fragments? Here's what an if statement is. So if we're at, for example, fragment 100, this is a block of code here, and as its final act, it tells the fetcher node which fragment to fetch next, either 101 or 102, the 2 conditionals for the if. And then each of these says, oh, next link me into 103, fetch 103 for me, because that's the one that comes afterwards. So it's a lot like you might see an if on a traditional computer, but there's never any fall through. In a normal computer, you've got a fall through case where if you don't branch, you will go to the next instruction. In this, a fragment is self-contained. It always executes from the beginning. You can't start in the middle of a fragment. And you always must, as your last thing you send out, nominate the next fragment to fetch. And that's how the program gets split into fragments in this. Yes. Old computers used, some Super in the 50s used to have lots of schemes for linking things together like this. The program is a linked list. So, here's an until, for example, and this is an example of a fragment just nominating itself. It gets to the end of 200 finishes, and if the condition isn't met, it may just say, oh, you know what the next fragment is? It's 200, so go fetch it again. And that will continue until finally its end condition is met, and it says, 201. I've numbered them consecutively, but they don't even, these are just numbers embedded in the program. So that's the beginning of program flow control, and that's kind of the easy part. It gets trickier when you want to do call return. So to do call return, you need to have a return stack, and I'll talk about the implementation of that, but here's how the fragments look on call return. So here, for example, is fragment 123. It's 1 plus, which does a tiny amount of code, not very much. It's like pushes 1 on the stack and does an addition. These are machine code operations. But this last operation, I've just called it exit. It does the stuff to pull the value off the return stack and then nominate that as its next thing to execute. So whatever is on the return stack, that's my fragment number that I want to execute next. Here's it being called. So in node 701, we want to call 1 plus. That's the only thing this fragment 701 does. What it does is it pushes 702 on the return stack, because that's where we're going to return to, and then it nominates this fragment, 123, as the thing to execute next. So 701 pushes its return address on the stack, just like an ordinary call instruction, and then jumps to 123, effectively, by saying this is the next thing to execute. 123 runs, exit pops the fragment number off the return stack, and that takes us to 702. So in an ordinary computer, we'd have call, and then it automatically returns to the following instruction. Here, we have to do it by hand, have to take this address of 702, have to choose the next fragment to be the one that runs after the thing that we called. So we hop from 701 to 123, and then back to 702. We've got call return. Depending on how deep the return stack is, it's completely general. You're going to start thinking about efficiency here, because each of these individual fragments has to be fetched, and it's quite a lengthy process to fetch them from flash, quite expensive, like a great big drum storage. Okay, so here's what the implementation, this is the external flash. This is the flash fetching node, which is just in the business of reading fragment numbers from here, talking to the flash, and then feeding the data out into this node, this decode node. Nothing's being executed here. These are just instruction words being sent out. D used to be a wire, but now does a few small decompression things just to keep the size down, because it's a very high cost for every bit. Every bit that comes, this is a 1-bit interface. There's 4 wires, but it only comes down to 1 bit at a time. So it's super expensive. So optimization isn't so much about reducing execution time, it's just reducing code size, because it's all about the size of the program. So these words get sent through D. D does a bit of decompression. X is always executing on this upper port. It's all sitting there executing whatever it gets from D. And that's where the actual action of the computer happens. X also has the data stack on board. So the parameter stack for the 4th machine is on X. R is the return stack. And R is also sort of, it's a lot easier if you're doing GA144 code to keep just 2 connections to the outside world. So a lot of these ports are either reading from one and then writing to another, or they're actually executing from one and writing to another. And you kind of tend, if you're talking to more than 2 things on the outside in GA144, it gets kind of juggling on the inside. It just does not have the resources to manage a complicated set of connections. X also has I/O connection. This is just a UART for now. It's just a write-only stream that I'm going to be demonstrating in a few minutes. It has a small RAM, which I'm not going to talk about much, which is about 300 bytes for doing scratchpad stuff. It's just for bring up. But 300 bytes is plenty for a small embedded 4th machine. You can do a lot in 300 bytes. What we have plenty of, though, is code size. We've got a whole megabyte of code, so there's no problem. So the data stack lives in X. It's about 24 words deep. The return stack lives in R. So for all of the return stack, like for something like RAT as a word, ask R what the for what the current top of the return stack is, and it comes back. When it does things like call return, it all is mediated by R. So in fact, when X hits a return instruction, all it does is tells R to take care of the return for me. Because R's not only got the return stack on it, it's also the one that's directly connected to the fetch node. So it passes the fragment number off the fetch node. So the return consists of X being told to do a return, pops the value off R's return stack, and R sends it onto F. So X never even sees the value. So it's everything's working in concert to build the 4th machine. One optimization that, of course, a lot of low-level 4ths do is they keep the top of stack in a register, Here we keep this top of stack in the top of stack on X. So X is all GA144s have an 8 deep stack. That's not really enough to run general programs, but it's certainly enough to do scratchpad stuff in X. So it's got a small stack. I think that's all. I did want to just talk about the instruction pointer. So in regular force, there's always something which is the instruction pointer, which is like the currently executing word. It does sort of exist here in the sense that there's a place in Flash that we're fetching from. And there's these effectively seek operations when we get a fragment number and we reseek to a different location in Flash. But really, the instruction pointer is completely implicit in just it's the current location from Flashes. With Flash, you just do a continuous read and it keeps on giving bytes starting at an address. And so that's the closest it has to an instruction pointer. There's no actual management of the instruction pointer beyond that. This is how it's laid out on the chip. There's the U. These are nodes, the fetch, decode, execute, and return stack, laid out like that. And then this is the RAM. This is a RAM controller, and these yellow ones are the storage, each 128 bytes. So it's 384 bytes total. And that's the whole machine. So now some examples of code. So plus. So we've got the data stack in memory on the execute node. So we can take the top of the stack and pop it using at plus. That fetches from that stack pointer and pops it. Now we've got the old top of stack and the current top of stack on the hardware stack. We can add them and just leave the result there. So that's the entirety of plus. It's very short. So the assembler for this also takes a couple of tags. These are just flag bits in the dictionary, which tells it that this is a word which wants to return on the end. It's just a self-contained word. And so that's what returns means. It means after this, do an exit. So we'll return to our caller. It also means it's inlineable. You can probably guess what that's going to mean in a few minutes. There's drop. One of the great things about GA144 is you can overflow the stack and it doesn't care because it's just a cyclical 8-deep stack. So to drop the stack, we just fetch the next thing and just ignore what was on the stack before. It's just irrelevant. Same with swap. It's a bit fiddlier, but we fetch. So now we've got the next thing also on the stack. We take the old top of stack and put it back onto the stack top. We swapped. So all of these things fit inside 18 bits of instruction word. These are each 5-bit codes, so they all fit in the same 4 instruction slots. So they're all effectively single instruction words. Okay, so that's the basic layout. You build up a fourth, those words run. Actually, after writing these words and getting the infrastructure going, it came up in a few days. It's pretty simple. It's really fantastically slow because it takes, so it was running about 100,000 fourth words a second. So slower than any of those Z80 systems that we saw at the computer fair. So it takes a really long time to fetch each of these words, do the return, come back, find out where it's got to go next, come back as it seeks through Flash. One of the things was that the Flash node itself wasn't very fast. The Flash node is obviously a giant bottleneck as it's fetching this stuff bit by bit. So optimizing that got a few factors, like a factor of 4, maybe quicker. But it's still horribly slow. Here's one reason it's really slow. If you have a word which is like this one, made out of 3 subroutine calls, you actually need 3 pieces of glue to be the return addresses for each of to glue these pieces together. So in compiling foo, we can of course just make a call to A, but then it has to return somewhere. And that return piece of code is what then is a place to return to, and then it organizes the call to B, and then call to C, and then finally it returns, and then that's the time to actually do the exit. So half the time it's actually just spent in these tiny glue fragments connecting the existing fragments together of organizing the call return apparatus. So this is a trick used by hackers. If you want to take control of a computer and you don't have very much code space to write out your exploit into, you've got maybe a few bytes, or if you're not allowed to execute code, because quite often executing code is a privileged operation, and so a lot of security systems prevent you from executing arbitrary code, you can call pieces of code in the existing program. For example, libc is a block of well-known code, and what you do is you just push a lot of things onto the call return stack and call various fragments of code, and every return that happens is like an indirect jump where it pops the next thing off the call return stack. So you can build up a giant list of things to execute just by pushing a lot of stuff on the call return stack, a lot of effectively entry points. And that's what this does. So instead of compiling it with these fragments, we just have a single compiled block for foo. What does it do? It pushes the address of C on the return stack. Same with B on the return stack. And then it just branches to A. So as soon as A completes, A is just a regular subroutine, doesn't know anything about what's going on. It just returns to what's on the return stack. Well, we've already set things up so that it'll then return into B. And the same for B. As soon as B pops the return stack, it'll go into C, C returns, and then we've finished. So using this, which is called return-oriented programming in hacker circles, then foo doesn't need these glue at all. It just turns into this piece of code here, which sets up the whole thing, and then it just branches to A and then goes on its way. It's sort of like something, it's getting some of the advantages of proper threading using a subroutine threaded system. Of course, it does take up space on the return stack. If you had 15 of these, it would push 15 things onto the return stack and go quite deep. That's why on the machine we've decided to make the return stack its own node so that it's got 50, which is plenty. That is one way of speeding things up. The other way of speeding things up is the obvious one, just inline it. So we've got a word foo, which is made of A, B, and C. We've got a dictionary. We've got all the code for A, B, and C available, and we just use a system of flags to indicate suitable for inlining or not. Just concatenate the code for A, B, and C, and put an exit on the end, and super fast, no call overhead. This is fine because while I was writing this, I was thinking, well, this is a terrible waste. As forthers, we're quite proud of the fact that we can fit things in a few K. But flash memory is very abundant. In fact, if the forth ended up being really enormously huge, if it was 100 kilobytes, which I don't think it will be, it's currently 12, but if it were 100 kilobytes, then it would use 1 cent of flash just at full. That's buying one flash chip. It costs a cent. So maybe in production it would cost half a cent. So bloating that and turning it into 200K of flash, which would be crazy amounts of inlining, would make it 2 cents. This is not a big deal. This is not going to be the major limiter on using this thing. So flash is cheap, and there's no point in economizing, so you might as well inline everything in sight just for the sake of performance. Okay, there's another optimization trick, and that is with inlining, you quite often end up with a word which a fragment which contains a lot of code and then loops back to itself. If everything inside a loop, a do loop, or an until loop, or a for loop is inlineable, then it can all be strung together and you end up with a fragment which loops back to the start. 200 here nominates 200 to be executed again every time it loops around. Happens a lot. If it's all just a straight line of code, you might as well just load it into the RAM of 200. It's just a flag in the instruction stream, not to execute it directly, but to load it into RAM and then execute it, and it fits in the RAM. Then you can just use a call instruction just to branch back to the beginning. Why not? Instead of going through the node fetching apparatus, you can put in a jump back to 0 and just restart the node's execution. So it's a sort of caching. You know that 200 is going to be the next one, so you load 200 and pay a small price for loading it and then executing it from RAM. Apart from that, there's no real change. GA144 doesn't care whether you're executing from a port or executing from RAM, so it's super trivial to do. The outcome, though, is that you avoid all of the overhead of fetching from flash, and it runs a lot faster. It's something like 300 times faster. So that's the big optimization. So the execution profile of the machine is kind of sluggish, except in this situation, when it's fantastically fast compared to the alternatives, and I'll demonstrate that. Okay, so that's all I have on how it works. Any questions before I launch into the demo, Brad?
So, I mean, you're sort of caching one fragment that way.
Yeah.
Is there some opportunity to do several more clever?
Well, yeah, I mean, when we were chatting about this over email, we had all sorts of fantastic So, yeah, there probably is. And there's probably something we can do in the D node. Right, the D node could have a side cache, maybe. So there'd be some tags in the F node, so it would know that they'd matched, and then it would send a match message into D, and D would have a storage. But I am literally waving my hands while talking about this. Opportunities for doing this are this happens quite a lot. This, and so that's catching a lot of inner loops, and do have some things we can do with other flashes that are simple optimizations. The flash that the Green Arrays board is old, like it's from 2010, 2009 maybe. And so it uses a really old flash, but later flashes you can actually run them in a mode with 2 bits per clock, and that would be double. So, so there's opportunities for speeding things up and making the costs lower. But yeah, caching would be good, but it's hard to make the GA144. It's hard to write native code for the GA144. So fitting some fancy algorithm into it is, yeah. It's a big challenge. Okay, any other questions? Okay, I got the demo on another window. Okay, so it's really live. It's running on this board here. So it's done as a compiler, and I'm editing the source file here, and this is the word that it runs at boot. And I'm going to do a little trivial thing, and Snap just dumps out the current stack and then halts. Okay. So what it did there was it compiled it, and succeeded. You can see it made about 12K of flash data. It wrote it into flash and then launched it, and we asked it to do 1, 2 plus, and it left 3 on the stack, and then that's the stack marker underneath that. So every execution run ends with that. So there you go. It's added 1 and 2. It's a 4th. Okay, so I'm typing backwards here. Okay, so don't read ahead. You'll spoil the surprise, because this one prints out that number. Okay. Does anybody recognize that? Yes. Yes, that's the fractional approximation to pi that's good to about 6 digits. So we've got a full set of math functions because Chuck on the colorforth page gives you code for most of the extended precision multiply divide operations. So that was kind of easy to add to this system, was just pulling in those. So we've got things like */. These are all running in 18-bit. It's an 18-bit machine and it's an 18-bit fourth. So there are some situations where it helps, but mostly it's about the same as a 16-bitter. So that was doing extended math. My next favorite thing is to do data vista calculation. So this is by Neil Board, or what was Neil's other name? Will Vaden. So it's an Easter calculator, and this is actually just plain fourth code, not really modified. And I just use it because it's kind of a classic algorithm. It's not very elegant fourth, but it gives things a good workout as far as math. So it computes the data vista for any given year. Then it leaves the year, month, and day. So that's April the 16th, was Easter this year. And just to give everybody a glimpse into next year. 2018? Yeah, so April 1st next year. So, yeah, it seems to be working. Okay. We've got loops, and this leaves a bunch of things on the stack. All right, so those are the dates of Easter working upwards for the next 4 years. All right, so it's a working form. Okay. Okay, so this is nested for loops, of course. You can kind of see there that that's 50 million iterations. So that inner loop will run 50 million times. Now this on, and I'll put.
Does that one get inline all of the ones?
Well, why else would I demonstrate it, Brad? Yeah, if it doesn't get inlined, it's really slow, because 50 million of these calls takes forever. But yes, it all gets inlined. So on polyfourth, which is the green arrays fourth, this takes 40 seconds to run, because it does about a little bit faster than a million words a second. And that next is a single word operator. So there's timestamps on the left since the previous one. So you can see it ran the whole thing in 1 second. So for that one, it's 40 times faster than polyfourth. This one, let's see. There's a few other. I actually accidentally destroyed my polyfourth, so I'm kind of limited in the comparative benchmarking I can do. Okay, this is a million operations of just putting 0 on the stack and dropping it. This takes 3 seconds on polyfourth because it's once again a million words a second, and that's 3 million operations. Push 3 million zeros, drops, and then next. Okay, so that's 65 milliseconds. So again, it's a sort of factor of 40 or 50. Yeah, I think I had another benchmark I was going to show. If these weren't inline, then it gets a lot slower. Okay, so I'll just reduce my expectations here, and I'll just do something like something which does a lot of calls. Oh, I've overflowed the stack, haven't I? Okay. There we go. So much more sedate when an actual call is involved, because now it's actually going back to flash and fetching it. That's, I think, it for demos. I mean, there's a lot of other things it can do. Let's see. We've got various other tests. Right. Yeah, I think that's it for live demo stuff. So next step is to, we've got the board that Mark made is a GA144 board with a more modern flash on it, which can do these faster readout modes. So getting that should at least double the performance of regular uncached code. And continue building out the fourth until it's maybe even a fully interactive fourth. There's no real reason why this compilation, it's kind of trivial stuff, just inlining is not hard. It can actually be self-hosting, but we'll see whether we actually bother with that. It's $1.60 in singles. Yeah, and it's a 128 megabit flash. They always quote in megabits to make them sound bigger. Yeah, so it's a 16 megabyte flash. It's a 128, right? Yeah. So yeah, they're cheap, and then you know the 256 model is just a little bit more expensive. So they're relatively abundant, and they're used everywhere. I mean, so. Okay, I think that's all I have for now. One thing is that this, with all of its hopping around, it's not actually completely suitable for fourth. Fourth, because of the way we factor things, it doesn't have a lot of opportunity for inlining. But there is a language where they inline like crazy, and that's C. So this system works much better for C on a register machine. That is where I should be standing right now. I am not doing a secret. Somebody should. They should do it like this. I'm available. That's right. That's right. So all that would happen would be that the R stack, wrong window, is that the R stack disappears and gets replaced with a register bank. That's the difference between a C machine and a fourth machine, really. X would, or maybe you could, if it was a machine with not many registers, you could put them on the X node. If it was a C machine, you just put, this is the register file, and everything else is the same. It would work great. All right. Okay. All right. That's all.
You lay the mic on me and I'll blather while Brad makes his way to the front of the room. All right, well, I'm Kevin Appert. I'm your program chair, and hello out there in internet land. I wanted to be sure you were aware of a couple of things that you may not be aware of. We have an email discussion list and an agenda page on the internet. So if you're running across this video and you want to learn more about us, Google is your friend. Just type in when is the next SVFIG meeting, and it'll probably take you to the agenda page, which has a bunch of other links to other SVFIG sorts of resources. We've got T-shirts, and Brad's going to tell you about that in a minute. We've got books from the early days of Forth and some more recent. You'll notice that our YouTube page is now, thanks to those of you that subscribed and otherwise voted your interest in our YouTube page, we've now got a vanity named YouTube page. So thanks to all of you, and thanks to Dennis, our stream master. Thanks to Dave Jaffe, our webmaster. And thanks to all our presenters. So with that cheerful blather of intermission, anybody need a bathroom call? Okay, we'll take that as a no.
I don't want to hear about it. Don't tweet me. Okay, who's the cashier for the shirts?
That would be me.
All about this at great length.
Oh,
Okay, well sit and watch, and then we can purchase after. Alrighty, so let's talk about T-shirts.
That's a great font.
Indeed, it was one of the default options, and I was looking for something, low key for this particular bit.
Said it wasn't available.
Indeed. So of course, we're back with another round of T-shirts because clothes make the man. And I thought I'd talk briefly about what's involved with this as we've started to do this now and again. Actually, in the theme of eclipses, which I'll talk about later, I've actually noticed a pattern in regular cadence. We seem to do these exactly 4 years apart for some reason. But in any event, the key thing with getting T-shirts online is to shop around, because there's competition and the prices change all the time. The vendor I went with the previous time, was no longer the cheapest vendor, as it happens. Weirdly, the vendor I did go with, as I'll talk about in a moment, was actually one that I had considered before. But there's tons of options. There's different kinds of shirts, different places on the shirt you can put stuff, different costs for different numbers of colors in the shirt, all kinds of things. If you come with custom artwork, of course, this is a challenging thing for the vendors, because they have to provide a mechanism for you to hand them your art. If you use things that they provide, text and whatnot, it's relatively straightforward for them. But there's a fun little range of different applications for you to upload your art, position it on the shirt and whatnot. They're going to have fun because a number of these are Flash based, and of course, as Adobe and several of the browser vendors have announced, we're going to pull the plug on Flash in 2020. So they're all going to have a fun time. A number of them are HTML5 based, and they seem to be migrating in that direction. So some of them will be prepared. They support a range of different formats. If you want sort of the best result, obviously you want a scalable format like an EPS file, or sometimes they support SVG, but actually the last time round they did, and this time they didn't seem to. So SVG seems to be falling out of favor, weirdly. You can, of course, do conventional image formats, but you want something sort of with as much resolution as you can possibly get. So I thought I'd talk about the history of what we've done with at least this round of shirts. I'm sure in the full history of FIG there've been a range of shirts, but at least in the time that I've been here, there've been three goes at this. Masakasa Hara back in 2009 said, we need to do some shirts, and we had the sign which is placed downstairs, and he snapped a photo of it, and he stuck it on a shirt with a company called Vistaprint, I believe it was, and I got a result like that. And there was some back and forth about, that what's with the gray stuff, because of course it's gray. And I think some folks actually chimed in and indicated that they like the gray. And actually looking at it now, at least it looks sort of a contiguous thing. Although one thing you'll find with shirts is that ideally you want to use as few colors as possible, because they'll ink them in sort of a successive rounds, and if you can use a solid tone, that produces a better result. If you have to do something multicolored, they'll have to use a dithering pattern, and you can get kind of iffy results in some cases. But fortunately, you can use GIMP to go and magic wand out the white region, and that's what we did, and we got something like that, which we now use that image in other places. And so that was our first round of shirts, and we must have printed about 25 of them. He got a promotional price and got them for $5 for the smaller sizes. And actually, this is a consistent pattern across all the years. There's always like a $2 difference for the extra large. For some reason, they figure they can charge that markup. And he got these on a white background, and since of course the shirts have faded and we've moved on. He also got some business cards, which I still got some of actually, and I think a few of us do, as a bonus. So in round two, this is where I had a go at doing this. I went with a company called Staples Promotional Products. They're connected to the Staples boats. Kevin is wearing a demonstration of this shirt. And this time round, of course, I was overwhelmed by options, and I foolishly, or maybe wisely, I'm not sure which, thought, oh, let's vote. And so one of the choices, so I went and took a program called Inkscape that lets you produce scalable images. And I went and took the relatively high-res but sort of finite image we had, and actually extracted from it a scalable image. And so I have a scalable version of it. And that let me do sort of in a nice way something that would have been challenging to do with just a bare image, which is because I had crisp boundaries for all of the colors, I could flip the color of the text without sort of weird artifacts. And so that opened up the possibility of, we could have a white foreground text and therefore a dark background. And so we voted on, did we want to do more of the white or blue and black? We also voted on a range of colors and had more choices and all kinds of fun. You had a fun name for the Caltrans Orange, indeed. So we used a Google form that time for it, and there's actually only like one section of 3 or 4 pages of choices. I had way too much fun with the forum, got back a bunch of numbers, and then we ended up with that. It was quite a lot of sort of, I don't know. It was an interesting process to do it that way. I used their Flash-based app to upload an SVG. I actually went with this company partially because of their price, but partially because they would. So the reason I used the SVG is that when I used an EPS file, which I also had, this is a PostScript file, the Flash app. So all of the apps for these sites make assumptions because they assume that you're someone who's got an image that you got from who knows where, and that you're not. Yeah, so you're going to stick it on there, and you're not going to know what to do with to separate out the background, because typically you don't want just a solid square, you want some region, and so they assume that things like white, they need to do something automatic to extract it, and so white confuses them. And at this time, their Flash app, the SVG worked fine with white, whereas with an EPS it did not. I mentioned in the comments, and so there's always a person. The other thing is, when because they have trouble with these people sending images and then not liking the result, they typically have somebody who knows a little something about it take a look at the files, figure out if this is going to be reasonable, and you get a little bit of feedback. This time I got a lot of feedback from them. They're like, oh, tell us the color numbers that you want exactly, and are these 4 fine? And then you mentioned you had an EPS file. Could we have the EPS file instead? And so that was what they actually finally went with. But yeah, there's lots of hassle with that white text, oddly. White seems to be, if you're trying to avoid trouble, it seems like you want to stay away from white in t-shirt vendors for some reason. So So we ordered a mix of sizes based on the vote. The interesting thing about this, and this is one of the downsides to that complicated form, people lied basically. Like, isn't there? This bared almost no resemblance to what people purchased. There were, notice, only 4 extra larges. They were gone instantly. What's that?
How about XX for large?
We still have one there.
Thank you.
For the blue, I mean.
Yeah.
So in any event, so in any event, asking people to reserve ahead, not so good. Oops. Come on. What's going on? That's not good. Come on. Not getting. That would seem. Come on. All right. So in any event, for round 3, the current round you see before you, I went with a company called Shirt. I weirdly enough left myself a note last time. I almost went with them the previous time, and for some reason I have forgotten why. Probably because I think I liked their uploading tooling or whatever, but their price was a little. You know what it was? They couldn't do the blue shirt. They could only do black. Weirdly. And so when folks voted for the blue, I couldn't go with them. But I sent myself an email and said, next time, if we're doing shirts, you should look at them. And strangely enough, they also had the best price. The company we went with last time had gone up quite a bit. I think they would have worked out to about $12 a shirt. Our actual cost this time was $10 for the smaller sizes and $12 for the extra large. We're going to mark them up slightly, and we did 15. We'll talk about where the funds will go in just a second. They have a weird pricing curve, as all of these vendors do. If you get like one shirt, you can spend $100 if it's custom. There's frequently, so there are options if you get like a plain white shirt and you don't use custom ink, so with these they produce a mask for each of these, and so there's a certain amount of sunk cost to produce even one shirt.
So
if you do,
it says 300 for some number printed white.
Nope. That's a screw up on the slide. I ended up doing $300 worth. So more. Why did I say 300 for? That's weird. Something. So there are a number of the vendors, not this particular one, will have an option to, if you get a plain white shirt and you're doing digital printing, where where the machine can go and basically it's it's printing the dot matrix version of it. Then you can get a very cheap sample, but it doesn't have the quality of the sort of nice single screen per color. This vendor also is really great in the sense that compared to Staples, which I think had I want to say a 3-week turnaround time, they had a 6-day turnaround time with no particular costs associated with that. There's all of them have, you can pay double and expedite, that kind of thing.
Talk about why we wanted a fast turnaround.
Oh, yeah. So, we had the one constraint that popped up on us was that Leon is going to take one of these to Euroforth, and so we wanted to have something by that time. So anyways, oh, come on. What's going on here? Let's hope that doesn't keep happening. Reconnecting. Come on. Come on. Oh, I know what's happening. I bet there we go. Nope, not that one. Okay. Come on. There we go. Okay. Of course, this time we had lots of choices too. In fact, this vendor also has options to. Kevin had floated the idea of pockets. We talked about pockets last time, which didn't get voted for. One option would be to print on the pocket. One constraint a lot of the vendors have if you have pockets is that the image needs to stay within the pocket. It can't sort of cross the boundary line. They don't want to deal with that. They also offer an image on the back. We considered at least one idea was Ting's logo that was used at Maker Faire and I guess other places. So we tried the look of that. They also support things on the shoulders, that sort of thing. But ultimately, this time we went with dictatorship and decided it was simpler, especially given time pressure, to just go ahead and pick something. I hope you're all horrified by the result. Indeed. So, so that's what we did. I did make a couple of fixes. In fact, this image is actually from one of the uploads. You'll notice that I corrected, in my opinion, the color of the poly to match traditional layout programs that will use a brighter red for the polysilicon on them. We ordered 30 shirts this time. This is closer to my mental recollection of what went more quickly, and we'll see if that proves accurate or not. But I figured I could better guess how large people are than they would accurately tell us and confess. We decided to go with $15, and then there's the question of what do we fund with the bonus money from this. So there's a range of possibilities. I figure we can sell the shirts and figure it out as we go. There's some folks that we could subsidize some gas money or around the donut delivery, and we actually are. Andreas is paying for rent for storage for the books, so we could put some of the proceeds. We'll have about $150 profit from it. We could fund our Meetup.com page, or we could pay for the the sea urchin. So we can talk about that briefly if there's anybody who has a strong opinion, but are there any questions?
Great. Thank you.
I set it up just the other day, so I'm going to have to fish up my phone to let you know, but give me 1 second and I will. Let's see, I installed the app.
This is 2XL. Yeah. Hold on.
We even have a 2XL in the blue if you want to.
There's more than one. Cool. What is it, $12?
15.
15, that's okay.
Yeah.
I don't know my size. That's good.
Thank you.
Let's see. How to properly wear.
Looks good. Let's see. Okay, now.
Here you go. There we go.
All right. Thank you.
Thank you so much.
Okay, let's see.
Yeah, it's cheaper than slightly cheaper than that brand, but it's like has a little bit price variance as well. In the days of global warming, am I prepared? I wish I had heard about this earlier, but look, I only heard one of the protest groups. Oh yeah, right. Just raise the heat, and those snowflakes will melt. Well, yeah, these snowflakes, that'll do it. We're early for the t-shirt sale. That's good. Yes. Give us a chance to I want to give the devil X. No. Okay. Oh, great. 16 is the most expensive. That's like spicy sugar. It's 4 megabyte, and it's like $500. Of course. It's about the same price as that brand.
So maybe you'll get some inquiries. Where's your online store?
Hold on 1 second. I'm recovering my password because I apparently did not remember my password.
Having something play here. Yeah, go LP. Actually, here's a good highlight.
Yeah.
Okay, so we're playing. Yes, thank you very much. I have a welcome for that. Now if you go look,
Okay.
you will not hear music. Okay. I hope you sell up. Well, not okay, okay.
Come on. Really? I have to type in the. Sorry.
No, just to make sure that, no, I'm correct. No. Yes, it takes a while.
It also has unlimited right endurance.
So having never received funds this way before, what is the information you actually need from the?
Oh, okay. I'm just going to send you emails 1, 2, 3.
Is it the email address? That's the. Ah.
You must be the last person on earth.
I know. I had only used Uber circa a year ago, so.
Have you seen Yahoo? It's a really good portal.
Ah, yeah. That is the right. That's right.
And then how is 15?
15, yeah. I at least went through the trouble of setting it up this time, as I had some other reason in between. But I remembered last time I was such a Luddite that could not receive payment in the modern way.
Since you're doing it, it's your decision. You figure it out.
The young people are using something else now.
Oh, of course. I received $15. All right, see, that's magical. As long as it flows that way, if it's like, oh, we lost $15, that would be upsetting, I suppose. So.
All right. More of the appropriate wardrobe.
Am I also presenting after this, or is there someone in
I
between?
think you are.
Oh, okay. Shall I commence?
I'll hold your hand.
All right.
I'll hold your hand.
Well, let me do my costume change.
You want to give Bill a T-shirt out of profit, or you want me to pay for it?
That's fine. Yeah.
What size, Bill?
Extra large. I love large. My wife says, no, you're next.
Really?
I started thinking, you don't know how to admire them, Bill.
Which is the smallest you have?
This. That might be the last medium, I believe. You were in luck.
All right.
Styling. Beautiful new ones. Beautiful.
Yeah, Brad does nice work.
Uh-huh.
And John Bible as well.
Believe it or not, in college, I actually did take a silk screening class and did these myself once. And let me tell you, it's hard.
Yeah.
Especially when you're doing it sort of old school with the photographic film.
Real silk screens.
Mm-hmm. And doing it with several colors is especially challenging.
Yeah, I hope to be able to say, okay, this is a well on a chip, and that's metal, and this is, but John didn't come through.
Yeah. No, I mean it is blatantly polysilicon, and that's metal, and I'm assuming the green is,
you
N type. But
You and I know this, but just to look at it walking down the street.
people don't. Yeah, it looks like water
Looking
or
at it
something.
on the website, I'm sure that there are plenty of people that.
It would be good to have the canonical description of it. So.
Yeah. And I think also John deserves some credit for being the originator.
Indeed, the image was without the image to start, we would have nothing. So. Shall we then?
So, did Bill get his?
I have no.
All right, let me fish this one out. X out, right? Okay. We're still
Oh, okay. We can wait. Waiting is fine. Okay. I don't particularly need more time. So, how much time is scheduled?
Oh, I think well, what's scheduled is 54.
So we want to get out. We want to be putting away our stuff on it.
Where's the You're there, you start at 15 to 6 and leave at 1600 or so.
Yeah.
You know, when you're done blathering and nobody has questions, just say, okay, thank you very much, we'll all plug and run off.
And we religiously vote to dismiss, which doesn't take a vote. Fortunately.
Oh, you may not lose. Oh! We vote with our feet. Okay. That's what I mean.
I did. I went to Albany, Oregon, as it says on the t-shirt. This is why the costume.
Oh, that's what the t-shirt
Yeah.
shirt is. Oh, yeah, it is. I couldn't read it on the other side of the room.
I had originally imagined charging something closer to that cost, and Kevin's like, oh, more, and then I would pay $20 for this. I'm like, well, apparently the price of the t-shirt is not what it once was.
Any particular ones absolutely go up at least $20.
Oh, with the white one's $5?
It's $5 at cost, yeah. You got a special deal with them. Promote your business, get better business cards, and
Okay.
and what in general, like the white t-shirt tends to be cheap. And it was a pretty good.
I think I still have one. I like this one so much better. And I like the black one so much better than that.
Neat. We'll have to figure out what the next one will be. Clearly in four years, because it's consistently 4 years between.
I'm kind of hoping
Which is not
going through these like in September.
Another batch report.
This was far more. I don't know if it was because I'd gone through the process of ordering or I just figured out just do whatever I want this time, but it was a whole lot. It felt a whole lot easier. Last time I remember it being I think it's also just the vendor didn't think they really wanted much handle. I know you're going to want to know which colors, all other colors.
They're just evolved.
They last time I think it was they kind of wanted to talk about it. I feel like I ended up talking to them. I think Mazda had a similar experience as well. They just wanted to talk about it.
Got a lot of people that say it doesn't come out, like you said, it doesn't come out what they expected.
And they don't get paid. And so therefore they want to talk to you first and make sure that you understand the limitations.
There's a class of printing press where just to flip the switch once and just zip out a few just to see how it's going to come out.
Right.
You have to print like you do that, you get 5,000, whatever it is.
Yeah.
It's like, whoa. Is this the fewest you can print? Yeah, pretty much.
Yeah.
And then there's HP is selling it. I think it's an Israeli company. They bought or outright. It's basically a printing press that can do one page. It's a printer that has litho quality and pretty damn good speed.
Oh, wow.
You can send everybody a magazine cover with aerial photo of their house from a database. You have a subscription address, you just print out a picture of their house. Recent magazine actually did this to prove that they could. They send all their subscribers an aerial photo of their house on the cover of Recent magazine.
That's intrusive.
Well, that was their point.
Right.
For drawings, J-size? Yeah. Yeah, those drawing printers are getting fewer and further between as people realize, you don't actually need big paper drawings to. You think that you saw the ones out in the hall there, the big. Oh yeah. That was one of the things I was thinking, if we're going to be doing like Maker Faire and things like that, Maker Faire and Computer Festival, it'd be nice to have a banner.
Yeah,
I like Things banners, although.
300. I think it's $300.
Wow.
For a banner.
Just find an internet company that can do it far cheaper.
Or the thing that they give you all the stand that you can stretch it out to, it's a banner, vertical banner.
Well, shall we?
Whenever you're ready.
All righty. Okay. So I've got the costume change here because I actually did manage to go see the totality and went to a small town called Albany, Oregon, and stayed on a tiny little parcel of ground that I purchased the right to be on for $100. It was, there was no room at the inn, so apparently no rental cars either, but unfortunately I drove up. So this, of course, witnessing this phenomenon, of course, inspired me to put a little thought into this space in general, and I figured I wanted to, better understand eclipses and how to predict them, and just improve my understanding of solar system dynamics. So. Eclipses, apparently, it comes from an ancient Greek word, eclipsis, which apparently, there's many translations, but apparently one means literally the downfall. So these were originally, viewed as very ominous signs. Apparently in 2300 BC, there's some record of 2 astrologers in ancient China being executed for having botched prediction of an eclipse. So it's been a long-standing problem. There's one of the earliest claims with a solar eclipse to accurately predict it, as Herodotus mentions this philosopher Thales having accurately predicted one, although there's some lack of clarity around how or whatnot. There are some indications that the Greeks had some idea how this works. There's this device that was found in the wreckage of a boat that, amongst other functions, the thought was that it could be used to predict eclipses. Apparently, by some estimates, it's not a terribly accurate device. A lot of the measurements on it compared to no. Apparently, one of the issues with it is that some of the measurements on it apparently are based. There was some searching about for rhyme and reason and things, and so some of the ratios are picked to be nice numbers rather than picked to be sort of numbers that you might observe. So.
Basically, got to be integers.
Indeed.
Or teeth on a gear, as we like to call integers.
So in any event, as time passes, of course, people did get better at this, and there's various indications about the Chinese and the Greeks having gotten sort of more clever about it. Around 1500, though, seems to have been when things sort of kick into gear. You've got some actual notion of how the solar system works. You've got the notion of the path, the paths of the planets better understood, heliocentric model and all of that. Lunar eclipses, fell much earlier. It's easier to predict a lunar eclipse, as I'll explain later, because the shadow of the Earth and the Moon is obviously much bigger, so there's a margin for error is larger. Whereas the solar eclipses are more challenging. There's tales of Columbus having told some folks in Jamaica that he was a deity, and because he could make the moon go dark and at just the right time, and got them to give him food in exchange for making it come back. there's apparently some indication that some of the success the Jesuits had in China spreading Christianity was around them demonstrating their greater accuracy in predicting solar eclipses, and there's a particular one that. So this was apparently something that impressed folks around that time. But as late as 1715, there's this eclipse that Halley predicts, and there were. I'll read the phrase here. Contemporaries published a pamphlet saying, this foreshadows the destruction of the fruits of the earth, the scarcity of corn and fruit, and the danger of a raging pestilence. So clearly, there was some lingering concern. Partially, this was because 100 years prior there had been some famine or plague that corresponded to an eclipse, and so people were in a sort of a negative mood in relation to them. So in any event, corn, yes, strangely enough. The notion, obviously, with an eclipse is that in the case of a solar eclipse, the moon is sitting between the sun and the earth, and of course everything has to just line up. So everything is basically needs to be in approximately a straight line, so-called SVFIG, I believe is the pronunciation, where they're lined up, and then the shadow cast on the earth is where you're going to see a totality, and in the penumbra you'll see a sort of a partial eclipse. Or if you sort of graze the surface, you might not get anywhere where you've got full totality. You can get the other way around, of course, a lunar eclipse where you've got the Earth in between and it's shadowing the moon. As I mentioned before, this is easier to predict because you can be off in your measurements, and the Earth is much bigger, and so you'll at least get it generally right. And the other thing is that the region that you observe the lunar eclipse is much larger. The center of it is in one location, but a huge swath of area can see the site. The key thing is, of course, is you need to be sure that you fall sort of where you fall in relation to the penumbra can affect what it looks like, and there's a distinction between a total eclipse and an annular eclipse where the moon is too far in, so that you get a little bit more of the fringe around it, and so you can't take off the eclipse glasses and look at it with the native eye. But to accurately predict these, we're going to have to get into a lot more detail with our model of the solar system. First of all, we're going to need to think about the actual orbit of the Earth around the Sun, and think about things like where the solstices and equinoxes are. And then the other sort of nuance, and actually back up here a moment, the key thing to observe here is that the Earth is going around, and in relation to our tilt, there's these 2 points on the equinox line, where the plane that the plane of the equator dips through the plane of that we rotate around the sun on.
That's the equinox. The autumnal equinox. That's where you're going into fall, and the sun's declination goes from positive in the northern hemisphere to negative in the southern hemisphere. And then in the spring, it's the opposite.
Right, and so those are the.
That's what defines when you have your equinoxes and also the solstice.
And at those 2 points, crucially, right, the sun is actually. That's the point where they're at the equator in relation to, right? And there's a similar thing going on with the moon as well. It's got a slight tilt. Its orbit has a slight tilt, and there are 2 points as well where it dips through the plane that it orbits the sun, and of course it's orbiting the Earth, but there's complications around that, as I'll go into. So. Historically, why does I have an extra bullet there? It's missing bullets in the other one deck too. So there's various ways to predict. One of them, obviously, is to just look for repetition. And this is, for a lot of astronomical things, this is what ancient people did. They would, they keep detailed records, and if you kept detailed enough records, you could see patterns. We do T-shirts every 4 years, this kind of thing. One of these is that if you take all of the various periods of involved is something called the Saros cycle, and this is sort of the notion that if you're talking about an eclipse occurring at a certain visible from a certain location, how long does it take to get back into approximately the same configuration in terms of where the Earth is in relation to the Sun, where the Moon is in relation to the Earth, and all of that. The trouble is, of course, the sort of closest to a nice number that exists is not an even number of days, and so that means that the Earth is turned differently. So if you really want it to be all, well, closer to the same, because you'll notice that is also not an even third, then you have to wait 3 times that period. But it does mean that if you keep detailed enough records, especially for lunar eclipses, this kind of thing can work well. You'll know that, well, if I saw an eclipse at this spot, if I wait this many days, and come back, I'll have something similar. The trouble is, it's only similar. The numbers are imprecise enough, and there's more complicated dynamics going on here. So what would tend to happen in ancient times is you'd have somebody predict an eclipse, and then it would be a little off, and they predict the next one and whatnot. So you'd have sort of drift from this. There's other simplified models. Various people have come up with, they've in many cases taken more detailed measurements and then come up with, here's a formula that if you plug in certain numbers, you'll get a list of all of the eclipses, say in the 2000s. The trouble is with these is that they're sort of fitting. They're taking the answer and then fitting it to the data. But the route that I decided to take, partially after a little bit of investigation and reflection, is to leverage data that's out there. NASA, and in particular JPL, has this ephemerides data that's readily available, and they actually have this information for the planets, but they have it also for all sorts of things, all of the spacecraft out there, various asteroids, debris, all sorts of stuff. But in particular, the planetary data is super old. I mean, there's by the time they start, they refer to these as development ephemerides, and they have a number associated with each of them. And around the 80s, they is when they started sort of more readily making them available. Going all the way back to 69, they were distributing these things on tape, and at that point they were numbered, 69. But at that point it was, there was a version called 19. It's basically been lost in the mists of history exactly when they started doing these things and in what form. But at some point they started being sort of forthright with these, and now they're up on an FTP site. And of course, what are they? This is basically taking a bunch of observations about the positions of the planets and the moon and such, and trying to make coherent sense of them in terms of what we know about Newtonian and later, well, not later, but progressively more correct relativistic models of how the solar system progresses. And so the idea is that there's too much n-body interaction going on to come up with some simple repetition model. Instead, you actually do a physical simulation and then try to tie it to your measurements. And they've used progressively larger and larger computations, and these are updated actually in a fairly regular cadence. It's very weird to go see the sort of the dates on this FTP site because a number they're frequently touched. The way that they're stored is interesting. I'm going to go into that in a little bit more detail, but they've, as I mentioned, they're progressively taking into account relativistic effects more. They're incorporating new measurements. I believe the figure of like 48,000 different measurements have gone into some recent versions of this, and then they encode them as Chebyshev polynomials. And the idea here is that this puts them in a form that makes it convenient to take derivatives on them, and it makes it convenient to represent them in a way where you sort of have the minimum loss of precision and can represent as much detail as possible in a small amount of data. The amount of data, to give you a sense, is, we'll look in a second because I've forgotten the number, but it's on the order of, I think, about 80 megabytes of data for the set that includes the planets plus Pluto plus the moon. They use a coordinate system that's centered on the center of mass of the solar system with the Earth subtracted out. And yeah, so, and actually, yes, speaking of the coordinate system, so they use equatorial coordinates. The x-axis points towards the vernal equinox. John, this is something I couldn't get a definitive clarity on, but I believe it's the vernal equinox as of like a particular date.
The vernal equinox is what's known as the first point of Aries. If you look at the sky, it'll be the constellation Aries. That's where the right ascension, which is measured in time, hours, minutes, and seconds. Okay, that's where 0 is. And then as you go around, in this case, where you go to the Y, that's where the summer solstice is.
But the thing that the subtlety I was trying to get at here, I'm wondering if you maybe this is too subtle. The direction of the vernal equinox, I believe, is as of a certain date for each of these versions of these data sets.
Actual position on the celestial sphere.
Okay, that was the bit.
Now remember, because the Earth is a spinning top, that point is moving.
It's precesses, yeah.
It's precessing and it's nutating.
Yes.
Not mutating.
Nutating, yeah. So it wiggles in relation to, yeah.
It's like a drunken top.
Yeah. So in any event, you've got the x-axis, and then the y-axis is, of course, still along. It sweeps out along the equator to 6 hours, and then north is celestial north, looking down on the solar system plane. So the plane swept out by the Earth going around.
Okay, that's a different coordinate system which you just described.
Oop.
Okay. The plane that you're talking about is where the celestial equator is, what you're looking down at. The orbit of or actually it's the apparent orbit of the sun. That's the.
Oh, I'm sorry. Sorry, I'm sorry. I flipped, but I confused myself here. Sorry. So it's sorry. It's the equatorial. Yeah, the equatorial. That's. Plane. Yeah, is the XY. The center is centered on that solar system mass. So in any event, as you'll see in a moment, you get surprisingly far for someone who's as confused as I am about the specifics of the data. So the time here is, of course, expressed in the form of Julian days. A number of years back, Ting had a fun exercise we all played through with things with Julian days, but this apparently dates to a classical scholar actually who was just interested in documents and describing the timing of historical events. He wanted something based at 0. He wanted a starting point that he reasoned about in terms of a bunch of periods, that some of which were sort of astronomical phenomenon, but some of them which were based on certain record-keeping practices of the Romans. And so he picked this start date basically based on this being the earliest sort of even alignment of all of these periods that was before any event that he was aware of in history, so that he could refer to them. He imagined, of course, centering time on Alexandria. When folks finally started using this for astronomy, they changed it to Greenwich. And then the idea is that you have an integer that's progressing, in your 24-hour period, but then the fractional portion is a day. There's a bunch of variations, and this is another subtlety where my depth of knowledge here is bounded. There's a bunch of variations in terms of how you take into account relativistic effects, and I believe there's I'm gonna botch the name, but there's a particular variety of this that is used for this data set.
Could be. It's been a while, but yes, Julian day is used for if you're doing eclipse and binaries, anything with time and astronomy. You have to put that in terms of Julian day.
Yeah.
And you will have accuracies out to like 6 to 7 significant digits.
Yeah. So as I mentioned before, the data is stored as these Chebyshev polynomials. The idea is that this is a particular series that you can fit data to. It's very nice if you're trying to avoid sort of ringing in data, where you get sort of wiggly edges at with higher order polynomials. The other nice thing is that you can very easily, they're polynomials, so you can easily find velocity and acceleration, or you can integrate them over time if you want to do that. And so it's stored as coefficients multiplied by each of these t0 through n, and they choose a variable precision for different phenomena. So for Mercury, you might use one number of coefficients, and for Mars another, that sort of thing. So there's many different variations of the format, but as far as I could tell, for these and for the bodies other than the planets, there's a newer format that is used. But the sort of core format for the planetary ones, which are very old, is the set of ASCII files, meant to be read by a body of Fortran. It's amazing to see Fortran code that's actually been touched as recently as 2016, sitting in this repository. There's a file with a header which has a bunch of textually named groups. One of these has indices or has markers in it to indicate, what start position do you find Mercury, at what start position do you find Mars, that sort of thing. And then it's just a series of doubles using the Fortran, one of the Fortran textual conventions. So it's broken down into a series of samples over time. That are one slice of the data, one record of the data, and for each of these they have a start and an end in Julian days, and then you have sort of the data for Mercury, and within each chunk they're further subdivided within that slice, and it's sort of an even cut. So you get like within that time period, you chop it into n pieces depending on how much precision you want, say, for Mercury. And similarly, for each of the planetary bodies, there's a different choice as the number of coefficients. So the Fortran code, which is sort of given as a reference implementation about how to look at and use this data, there's actually two separate programs. One of them takes this textual data and converts it to a binary form. And the main reason they seem to do this is for speed of lookup. That way, the ASCII file, you have to stream through it to find a particular time. The binary data, if you do it in the way that the Fortran code is set up, you can arrange so that you can just seek to the appropriate position, because the slices, I believe, are guaranteed to be equal sized. Interestingly, though, I was noticing in the slices that they seem to have sort of weird overlaps. Like they include the last record, a duplicate of the last record of one range as the first record of one data file as the last record of another. I'm not quite sure why that's done. It's probably something to do with each data file contains 1 century's worth of data. And I should say, by the way, that this data, because it's a simulation tied to these measurements, they can run the simulation forward and project into the future, or they can run it backwards in time and project into the past. And so they have data. They've redone these. They typically will redo them when they have a good reason. Various probes and whatnot will prompt them to redo the data with an eye to sprinkling in more measurements of a certain type. And the typical range is from 1550 to 2550. The code it's weird. Yeah, it's weird in 2016 to see code that both is being touched for various reasons, but is also making accommodation for VAXs and whatnot. It's a strange.
One of the big problems that they have is they still use Fortran code. Some are starting to do Python, but they have to do it in a private setting so no one watches them because they're afraid of having to become a registered sex offender.
So there are in this repository there are some copies of various a couple of other language implementations for access to the data set, but you can kind of on the one hand the C version of where the Fortran one is a couple of files and maybe a few few thousands of lines. The C implementation is ginormous. It for some reason is takes something on the order of I think it's like 100,000 lines of code, and yet it doesn't actually support all the modes that the data is in. So a lot of this is just boilerplate to manipulate records and whatnot. There's a Java implementation that for some reason only handles the Earth, the Moon, and the Sun. And then there's references to other implementations. The other thing is you get the sense that different languages have had different sort of amounts of love at different times for different purposes. But the intention with the Fortran one, and partially why I think it's still getting touched, is that it has its sort of test code that I didn't mention this in the slides, but in addition to the headers and the data, they also include a sort of a test file to say, okay, if you're going to load this data and you think you've got software that can read it, here are some raw values. Go look up this time and this planetary body and confirm you're getting this measurement so that you know that you're decoding the data correctly. The Fortran code is structured as that test, but the idea is that you could pull out the routines in it to use in whatever software. And I get the sense that there are a number of other packages that build on this to do this. And you'll notice that in a number of NASA and JPL's online materials, they will use the codes from this Fortran code, like the number values for the planets and the moon, and literally in the web UI, that kind of thing.
Exactly. That's because of Fortran.
Yeah, well, exactly. So the way you go about actually applying the data, if you want to look up a particular measurement or prediction, rather, you find the record that contains it. You could, if you deduped the records, you can just seek to the right location. I didn't want to deal with deduping it, so I just, for my implementation, I ended up just putting them in order and doing a binary search. It's not enough to care particularly. And then within that chunk, or in that record rather, you need to find the start offset to the body of interest, and then chop up that time region into the appropriate number of segments for that planetary body. Within that region, they scaled the Chebyshev polynomials so that instead of using Julian days, they recenter them in each of those subranges from -1 to 1, presumably a precision-saving affordance. And then you multiply out the coefficients and tally. This is interesting coming from like a graphics background, because where clearly the theme here is to make it very convenient to quickly look up a fit of data, whereas a lot of times in graphics there's a tendency to assume that you have sort of uniform samples, and here you're coming with a bunch of amorphous samples, various inputs from different probes and different observatories, and then you have a curve that fits it, and then you use that as a reference. It's a kind of a different way of looking at things. So progressing on now, what I wanted to be able to do is then to do something with this data with eclipses. So I need to show a world map. I want to be able to show markers for where the celestial bodies are, and then I wanted to use the keyboard to move time around and then print various values. I reused a bunch of code that I had, so I decided to use GForth for this purpose. I had some old code around a font library that I'd done a while back that had code for doing X11 graphics and keystrokes and mouse events. And then for anything where I have to actually display numbers, I just go to the console. So for the map, I decided to use a cylindrical projection, or what the heck? Oh, equidistant. Yeah, sorry, I read that wrong. Equidistant cylindrical projection. This is just sort of the easiest projection you can imagine doing. Latitude and longitude are the X and Y axes, essentially. This goes back to Marinus of Tyre. And you get a map like this, which is squished in interesting ways, but is very simple to deal with. If you have a latitude and longitude value, you can go find it, and that's sort of easy to find the correspondence. I have the same problems that Ting does, of course, coping with images, given that we went for standard libraries to cope with images in Forth, so I pre-converted the map image to a raw binary using a program called ImageMagick, which is good for this sort of thing. I, of course, needed some facilities to operate on the data types involved. I came up with a sort of a simple three-dimensional vector type and some add and subtract ops. Why did this recapitalize those? Okay, that's unfortunate. Dot product and some duping and scaling and this sort of thing, loading and storing. And then I needed, the other thing I'm going to need to do to actually find eclipses is I need to do some ray-sphere intersection. So I came up with a set of words to let me pick a target and an origin, describe a sphere that I'm interested in its position, find the intersection, and then reference the points. So there's some fairly straightforward math you can do to do ray-sphere intersection. You find the formula for a line based on time, and then the ray moving out, this sort of thing. And then if you plug those into the formula for a sphere and you jiggle around, you can factor this into a quadratic quadratic equation. You can find the roots of it. If there are no roots, then you're not intersecting the sphere. If there are 2 roots, then you're punching through the sphere in 2 places. If you hit just the edge, you'll get a single root. So how am I going to detect an eclipse? Well, I'm going to cast a ray from I'm going to use the ephemeris data to find the positions of the bodies. I'm going to cast a ray from the center of the sun in the direction of the moon and find out where it intersects the sphere of the Earth. And then from that point, I'm going to take a direction out from the center of the Earth, and that will give me the direction of the point on the surface of the Earth that I'll see the eclipse at. And notice that this, in terms of the data that's in the ephemerides, I'm using the position of the sun, the position of the moon. I'm, of course, by the way, all of the data in the ephemerides is in terms of center of mass, with a couple of weird exceptions. And so I'm cheating and treating the center of the object as if it's equivalent to the center of mass. There's, in practice, a small difference. So for the sun, I don't need anything other than that position. Same thing with the moon. But for the Earth, in order to know how big the sphere is that I'm raycasting on, I need to have some value for the radius. And so that's the one constant I'm using that doesn't come from that ephemeride set, is the size of the radius of the Earth. I did mention this before. The ephemeride data is in kilometers, although weirdly, all of the library tools around it, including the Fortran code, goes to great lengths to then convert everything into astronomical units for reasons. I'm assuming this is an astronomer thing.
Yes, it is an astronomer thing. We do things backwards and upside down. That's because, and also being astronomers, we only know how to add and subtract. When it comes to multiplying and dividing, we kind of fall off the rails. And the reason is dynamic range. You don't even know what I'm talking about.
Yeah. You're going to lose your range pretty quickly.
To the brightness of our sun, as seen from the Earth, that's like minus 24 magnitude. Well, now, because of our orbiting telescope, it's seen down to magnitude 50, which is extremely dim. And that's a logarithmic scale. So that's what, 75 magnitudes, something like that. If you divide by 2.5, let's see, that'd be like 25. That's a number that's 10 with 25 zeros. So that's the kind of dynamic range deal. So it's like, why do multiplication when you take the log, you can add, that's a lot easier.
Interestingly, I suspect this is why there's also, and I glossed over this detail, but the format, of course, is rich with doubles. There's a fondness for precision again. And the other interesting thing is that apparently for the underlying simulation the ephemerides are based on, they've even gotten to the point that for many of the simulations they're actually using 128-bit floats because they want the quad floats because they want the extra precision. Let's see. So there's so a bunch of nuances here, right? I've mentioned the radius of the Earth. The other one is that notice that this approach, and it actually didn't intend this. In fact, I originally tried a slightly different. I had a slightly different approximation for the eclipse, where I was using dot product to see how close to linear everything was. With that approach, it only found the solar eclipses. But one thing I didn't realize until I'd actually run the program is that this approach, notice, also works for a lunar eclipse, because if you're casting in the direction of the moon, that same ray will intersect with the moon, and so you actually get both sets out with one approach. The partials can be trickier because, of course, here I'm just focused on that center line, whereas if you actually cared about sort of what region can actually see the eclipse, or which region is in the eclipse but outside of the penumbra, then you've got you've got more calculation to do that I did not bother. There's other nuances like the nuations of the Earth and things that are in the nutation rate. Nuation or nutation?
No, there's a T between the U and the A.
Oh, did I botch the spelling? Okay.
Yes.
Okay.
Yeah, I can understand because you have nuances.
Yeah. Okay. Well, that's a typo in the slides. I'm going to show the demo program. It ended up being relatively small. There's it's like 700 lines. There's I ended up like the Fortran program with a converter that reads through the ASCII text and produces a bunch of binary data. In my case, I actually load it up into a bunch of blocks and use an offset there. The core of the user interface is in there. There's a bunch of the calculations around extracting the data from the ephemerides database in this file, and then this is that graphics library I borrowed. For a while, I actually tried to just use Julian days for everything because that's sort of the natural number format, but they're not very fun to work with if you're like trying to look up historical dates. And so at a certain point, after I kept going back and forth to a web-based thing to punch in a Julian day and find out what date is this really, I went ahead and put the effort into to do a little bit of code to convert from Julian days to dates, so I could print out the date that I'm at and not have to go look that up. A bunch of facilities are in the arrays and vectors, as I mentioned, and then another part of that graphics library. So before I go to the demo, I'm going to mention that, of course, prediction of eclipses is challenging. There was that 1715 eclipse that's sometimes called Halley's eclipse, and this is because Halley explicitly went ahead and predicted that a particular eclipse would cut straight through England. We'll go and see if we can go back in time and look at that one. However, I will point out that this can be challenging. As it happens, despite the attention that it got, he was off by 20 miles. So caution. We'll do the questions in a sec, but I've got a demo here. So let me just quickly go on a little tour. So as I mentioned, there's this Julian day calculation, which is just take what's on Wikipedia and punch it into Forth. That's nothing particularly deep. There's ray intersection here, building on vectors, which again isn't particularly challenging. Let's look at the converter. Just goes through and processes these data files. Just to give you a sense, let's look at one of the data files here. So like this is sort of what that raw data, ephemerides data looks like. They're broken down into these record chunks where they have an index, one index like everything in Fortran, and then a size of the record, and then just a ton of doubles. The header actually has some additional information. There's a few different sections to it and some constants, but the most important bit to get out is this table of for each planet. What's its offset in the record? How many sections is it broken up into? And then how many coefficients? And that same thing I've replicated here. Rather than parse that particular file, I just put those numbers in line here because one thing that file assumes you implicitly know is that for the planets you have three coefficients for position, or sorry, three components for X, Y, and Z, but for instance, nuations are in is it nutation? Nutation. You sure about that? Okay, I thought I could go to. And then the moon, they also provide a three vector of I guess it's orientational things called librations, and so I pulled each of those out into a single word. So when you run the Mars word, for instance, that will leave on the stack three floating point value. Sorry, you call another word to set the Julian day, and then when you call Mars, you get the three XYZ values for Earth. What that lets you then do is over here in the eclipse calculation, I'm able to obviously go through and draw, for example, the sun and pass in the time and convert that to latitude and longitude and put that on the map. But if I want to actually find eclipses, I cast the array from the Earth to from the moon to the, or sorry. Oh, this is another weird nuance. So for the moon's position in this database is relative to the Earth as its center, which is distinct from all the other bodies. They're all sun relative, and so I end up taking the sum of the Earth's position and the moon, and then casting from the sun to that, which is casting towards the moon, and then having a sphere centered at the Earth with an Earth-sized radius, and then checking for an intersection. If I find one, I cast out a point from the Earth to that intersection and then draw that on the map. So let's give this a go. Let me shrink this down. So I set as the start point the eclipse that I just managed to see in a few days back. And the way this works is that I've got various keys that let me move forward time. On the right here, you'll see that this is, August 21, 2017. You've got the Julian day. And then when you're in a region with the eclipse, I show the latitude and longitude just as two numbers in degrees. The moon and the sun that's their position projected out from the center of the Earth. And is there a name for that?
If you were at that point, the body would appear straight above you.
You're right. That's right. Okay. That's the right way to put it. And whereas the shadow that they cast is over there, that's of course tricky because there's small differences can influence where the shadow gets cast. So as I move time here, you can then see the sweep of the eclipse. And of course, if you go far enough, it blinks away because you're no longer in existence. And similarly, you go backwards in time. And so the next thing I did is I added a pair of keys that let me seek forward and go looking for the next eclipse. And so I just move forward time in small increments and look to see, am I in a situation where there's an intersection? And I can use this to then jump forward, so we can then push and jump forward to the next one. And as it happens, the next one is a lunar eclipse. And here you'll notice that the sun and the moon are at 180 degrees apart because they're on opposite sides. Because now the Earth is in between. And that center point, of course, unlike a solar eclipse where it's a very narrow, 100 kilometer band, with the lunar eclipse, there's quite a region that you can see it in. Because it's sort of anywhere that you would have visibility to the moon from there. Give or take, there's also the nuance that you have to, anyways. So that moves around. But let's skip ahead and find another solar eclipse. And it's another lunar one. And that's another lunar one. And in order to try to capture partial eclipses, I give it a little bit of slack in terms of the numbers involved. Although it's not 100%, like if you go through a table of partial eclipses and compare it with the numbers I'm getting, you'll miss some. So this is one that's coming up that goes down here and then cuts through the bottom of South America. There's an opportunity to see that one in July 2nd, 2019. We can progress forward a little bit. And there's another one on, this is lunar, let's see. And here's another solar one that's coming up in December 25th, 2019. And it cuts across like this through Mexico. But let's now try the fun exercise of. Oh, actually, let me show one other thing before we go on to that. Just for fun, of course, I stuck an option turn on the. What was the name for that again, John? The position where they're directly overhead. This puts in all of the.
It's what's known, if it's a sense, the anti-solar. I think it's called the anti-solar point. It's the point where
it's
directly. It's at the zenith.
Ah. So I did the same with all of the planetary bodies, and they're, Mars is red and Uranus is blue and green, and this is them. And one fun, of course, going slowly through the day, things just move across the sky. Actually, before we show that, let's just concentrate on these a moment. If you go, through the day, it progresses like that, going hour by hour. But if you skip forward by exactly a day, you can also see this sort of neat phenomenon of the moon oscillating at its 30-day period in relation to the ecliptic, and similarly the sun doing the same thing in relation to the year. And this is sort of zooming forward through time. You can even go We go faster. We can go even faster. Now you can see the sun zipping up and down in that pattern. So in any event, let's now use our time machine to go back to, actually I'm going to jump back by centuries here, back to 17. I would have loved to go, there's an event, that Columbus event is in like 1500, but unfortunately the data only goes back to 1550. So, I'm going to go back to 1714, and then going to skip forward to find the appropriate eclipse. And that's still in 1714. And 1714. And here, okay, so here it is on May 2nd, although this depends on what time zone you're in. This is if in England, it would have been May 30th. Interestingly, one other thing about Halley's eclipse is England was still on the Julian calendar at that point. So they actually considered it some date in April at that point. Now, I'm going to sweep through and show this, and tell me what's wrong with this picture. A little bit off. Exactly. And it's got the right date. It's got very close to the right coordinates, but it's off by just a smidge and misses England. And I'm a little mystified what's going on. I suspect that the number of possible problems that could be at play here. I think the reason that and I've noticed going and comparing the dates that I get, that they're fairly accurate compared to lists of eclipses that I can find online. But I think the issue is how I am finding that intersection point rather than the presence of some kind of an intersection. So I think the issue, couple possibilities. It may be that I'm using a sphere as an approximation. That may be that probably plays a role. The other thing I'm less certain of is, so they include data in this set around, yes?
Yes, and the other thing is, do you remember that picture you showed where you had the sun and a vector going through the moon, going into the Earth?
Yeah.
But remember, there was an offset from the center of the Earth. That might be the problem right there.
So I'm finding the intersection, and then I'm finding the vector from the center of the Earth to the...
Yes, yeah, you got to do a little bit more math.
Okay.
I was going to mention something.
Okay, yeah, we should talk it over. So I'm guessing that my calculations are off. I'm sure that what's saving me in terms of actually being able to accurately find these eclipses and not being so accurate in terms of positioning on the map is that the underlying data set is, of course, really good and has all of this precision into it. And so, and when I first did this, I initially didn't worry about the problem of showing them on the map, and I instead just said, okay, let me cast a vector from take a vector from the sun to the moon and the sun to the Earth, and then dot product them and see how close they are as to go look for eclipses. And that was fairly accurate as well at finding them. In fact, it was a little bit better at finding partial eclipses on the fringes because you could be more generous with the. But of course that's basing it on points that from the data set we know are super solid. Whereas my doing the raycasting is I think where I'm running into mischief. Let's see. So I was going to put the planets on here. And of course, you can move the planets with speed and see what they do jiggling about. But of course, this doesn't make a lot of sense because this is all from the point of view of observations on Earth. And in some sense, though, I think this highlights why it took ancient astronomers so long to figure out what was going on with our solar system, because this is sort of not exactly intuitive what you're seeing here, right? And there's patterns, but they're not necessarily obvious. And of course, they were looking at even fewer, right? This includes Uranus, Neptune, and Pluto, and they could really only see up to Saturn. So, in any event, are there any questions?
Looks cool. I mean, because normally what you get is, you saw that picture where it showed the eclipse going through England. Because normally what you get is the path of totality, and then you get what's called the first contact. That's when the shadow first touches the Earth, and then it splits, and one shows
Yeah, there was something I was trying to figure out. Is so they have when they apparently have some standard. I wasn't able to find a sort of an obvious description of what where this comes from. But it sounds like there's a notion of picking one of the points along the path of the totality that you use to classify it as the center of the eclipse. And I don't know how they decide whether it's time based or some positional thing or something. Whether it's the center of yeah.
Yeah, I understand that.
So. It's interesting. The other thing I found is that there seems to be a very small community of folks that care. It's like a lot of the folks that did the various tools that you see online will specifically thank this particular guy at JPL, and the same guy comes up in several places, and literally he's the guy that ran the numbers for the stuff that they have up on NASA's website for this last eclipse. So it's a pretty small community of folks that. The other interesting bit is that they I haven't quite figured out. They keep around these different versions of this data set, and there seems to be a preference in some cases for not using the freshest version of the data, and I think it's because different runs they emphasize different things in the simulation, or they had greater precision with some of them, and.
I mean, still using Fortran.
Yeah.
Well, here's the thing. A lot of them, you and I know, and everybody in this room knows that you must initialize your variables before you do it. Well, these astronomers go, that's too hard to do. And this is probably the same reason why someone discovered chaos with weather simulation, because again, idiots didn't initialize their variables, and if whatever random variable number was in there, we'll use that, no problem. And you get different results.
I also found references to with some of the use of old data sets. Sometimes it was based on like comparability between different. You want to do something, you don't want to change your data set out from under you. But the other thing that was interesting was I did see some mention of we're using a DE200 because that's the largest version of the data set that this particular package can handle. And if you get to the newer data set, they can't fire up whatever DOS program they are doing this in. So.
It's the computer science, computer engineering aspects of programming that a lot of astronomers just, literally, halt, catch on fire.
They also have, they're very, very, very committed. They worked for years with this data set.
Yes,
okay,
exactly.
Why should I use someone else modified it, added some new stuff? But I don't understand exactly what they did everywhere in here. So I'll continue using this data set.
Yeah. And it does seem like sometimes when they, the other thing is you look at the notes for these and like, what is it, the latest iteration of it, of all things, they upped the precision for Pluto because they were sending out New Horizons. So they put more precision over on Pluto and less on some of the others. So it's sort of I think the different data sets emphasize different planets more or less. So.
I think to think about more simplistic view of this thing, because in Chinese language, we have three tracks. Okay, so it's the red track, which is the equator. That's the Earth rotating, and then there's the yellow track. That's the sun. That's the track the sun moves. And then there's white track, which is the track that the trace that moon moves. So it is these three tracks that how they overlap with each other. Especially at the first of the moon and the 15th of the moon, and the first of the month and the 15th of the month.
Right.
And if the white track overlaps with the yellow track, then you got eclipse, either solar or lunar. So I think, if we have these tracks, the sun, the track of sun, we all understand from the plus minus 25 degrees above and below the equator. I don't know. I think the moon track most similarly.
Yeah. Well, I mean, in fact, literally, you can see these. Oops. Let me give that a second to warm up here.
They're similarly, but with a different periodicity.
You can watch. Oops.
Yeah.
You can literally see. Oops.
So what you need to do is to see.
See the oscillation there with the moon at one period and the sun at another.
If these two tracks meet with one another, then there's a possibility of eclipse.
Right. In fact, I imagine we can probably watch for. Oh, not quite close enough.
Yeah, it has to be quite close in order to have eclipse.
Oh, and look, there it goes, right? And you can suddenly get the shadow. So you've just described, right?
Yeah.
Right. That is in fact, and I think the thing is that is, my sense is that's what a lot of the ancient astronomers did, and of course the challenge is precise measurement of those is where you run into challenges, and it's much easier to the margin for error is of course smaller in their position if you're worried about a solar or a lunar eclipse rather. But
of course, then predicting, you have pretty good idea on when this eclipse will occur, but where it happened is much more difficult to predict.
Yeah.
And that's what you have shown.
Yeah.
Okay. A comment from the audience.
Oh.
Brad, absolutely great work. Also from Bob.
If you stand next to him, they'll hear it out on the interwebs.
Indeed.
Well, on the interwebs, you can see. Brad, absolutely great work. Also for me personally, very useful to see such things done in a standard fourth.
Yeah. Thank you. Yeah. It is up on GitHub now. If you look for fourth eclipse, something or other on my. Yeah.
Except for eclipse.sh. Yes, you can't check it in.
Wait, which?
The shell script that runs the actual thing.
Did I fail to check it? So you need to run. Eclipse.fs should be executable and has the shebang at the top. I don't know if you've noticed this. The G4 have a fun. They include the shebang as a word that gets that will comment out the line, and that's convenient because if you do it, you're allowed in Unixism to have a space there, which people frequently do not do. But if you do that space, then this will parse cleanly and let you have an executable FS file, which is handy. You have to, before you can run it, you have to also run setup sh because that does the download of the data set and the conversion of the image. So. Probably. There is a README, but it doesn't say very much. I think it says run sh or setup.sh and then run blah.py. So. Actually, in fact, I know I have the wrong thing in there, I bet. Because I bet it says, it says Eclipse sh, which is wrong. You had actually read the instructions and then.
No, you did the right thing. Okay.
Thanks. Wait, did I just say .py? I think I might have said .py.
Yeah,
I think I did. Okay. Been doing too much Python.
That's what I thought.
FS. There we go.
There we go. That's better.
All right. Any other questions? Were you able to? You're downloading the data, doing the conversion.
It's called nuation and the mutation.
I need to look up. Okay, now I'm dying to know that. Is that really the?
No, that's not a word.
Aha. That's the word. All right, let me fix my. Aha. Well, I'm never calling that word in here, so that's why. So, and we could even fix the slide deck. What's that? That one was not actually being called, actually, which is why, fortunately, although I could fix, I could, yeah. Well, I tried to make good use of that. Let me find where's the nuances slide here? This one. I can fix the, oh, it even was telling me that, no, it's not the word nations. Cool. I was going to say something else, but I've forgotten. Oh, well. Yeah, anyways. That's all I've got. Thanks, everybody.
Thanks for attending. See you next month. Goodbye.